Hello there, this is an Algebra 2 video. It's Chapter 8, Section 3, and today we'll be talking about graphing reciprocal functions. And I'm pretty sure you guys know what a reciprocal is. It basically means that you flip over a number. For example, the reciprocal of 2 is 1/2. The reciprocal of 1/2 is 2. So in this case, we're reciprocating a function. So we take a linear function, and so it says here where a of x is a linear function, a of x cannot equal 0. That's because you can't divide by 0. But you take any linear function and you basically reciprocate it. So something like y equals mx plus b, for example, would become 1 over mx plus b. And so what I want to have for you here are some basic characteristics of a reciprocal function. And we start with the parent function, with the most basic linear function is y equals x. And if you reciprocate that function, meaning you flip it over, you get f of x equals 1 over x. So this is basically our parent function for reciprocal functions, and the graph of that function is going to be called a hyperbola. You know that we talk about quadratics and we call those parabolas. It's a very similar word, but this time it's a hyperbola, and there's basically two parts to it. Sometimes they refer to those parts as branches. So here is one branch, or here's the other branch, or arms, or whatever you want to call it, but together we basically call them a hyperbola. And so then we have domain and range. For this function is basically all non-zero real numbers. In other words, when it comes to domain, which is the x values, the x value can never equal 0, so you'll notice here that the graph never actually hits the y-axis. And likewise, on the left and right, the graph never crosses the x-axis either. So basically, the x values can be any negative or positive number, it just can't be 0. And the same thing for the range. It can be any negative y value or any positive y value, but the y value is never 0. And so we have asymptotes. Asymptotes are basically imaginary boundaries where the graph approaches but never crosses. And again, because of the domain and range issues, you'll notice that the asymptotes are likewise x equals 0 and y equals 0. If you were to draw the imaginary boundary of x equals 0, it would basically be a vertical line right here. So it's again a boundary where the graph approaches but never touches. And then also you have the f of x equals 0, which is the same thing as y equals 0, is a horizontal line, so a horizontal boundary where the graph again is approaching that line but never actually crosses it. So you have both a vertical and a horizontal asymptote. Intercepts in this case are none because it never crosses the x or y axis. And then values that are not defined, going back to the domain, values that are not defined are when x equals 0. In other words, we can't have x equals 0 because if you plugged in 0 for x, you would get division by 0, and we definitely want to avoid that. So those are the basic characteristics of the graph, and so now we're going to get started with our example. So in our first example, we are trying to determine the value of x for which the function 3 over 2x plus 5 is not defined. And I mentioned earlier that the function is not defined. When it comes to reciprocal functions, your biggest place to look is division by 0. You definitely want to avoid division by 0. And so since we can see that the bottom of the fraction is 2x plus 5, we need to figure out when will 2x plus 5 equal 0. That's the question, because we definitely want to avoid that situation. So we subtract 5 from both sides, and we get 2x equals negative 5, divide by 2, and so it turns out that when x is negative 5/2, the bottom of this function will equal 0, and therefore you'll have division by 0. So this is the value of x for which the function is not defined. It's not defined at x equals negative 5/2. All right, so really basic. And easy to do. So now we're going to have you try this example. Again, just remember that the bottom of the fraction cannot equal 0, so you define those values and then state that that's where the function is not defined. So then we're going to go to example 2. In example 2, if you want to look at a better graph, you can definitely find these graphs on page 546 of your textbook. I tried my best to graph them as accurately as I could, but the book also has these in there so you can look at them if you'd like. It says identify the asymptotes, domain, and range of each function. So we're just looking at the function and trying to identify the asymptote. Remember, the asymptote are those imaginary boundaries where the graph approaches but never touches. So for our vertical asymptote, we want a horizontal asymptote. And when you have a vertical asymptote, the equation is always going to start with x equals. And we're trying to find where on the graph the actual function is approaching but not crossing that line. So it looks to me like that's happening right here at 3. And you can even draw this imaginary line. Let's make sure I got that right. And see, you can see that the graph is kind of approaching but never crossing this x equals 3. And you can also see that if we were to solve the bottom of this equation, x minus 3 equals 0, we would get x equals 3 as well. So our vertical asymptote is the equation x equals 3. Our horizontal asymptote is going to look like it's still the x-axis. The graph has not been shifted at all, so it's still the x-axis. So that's going to be y equals 0. The other part of information that they're asking us to find, also going to draw in here your horizontal asymptote as well. But the other part of the instructions state for us to find the domain and range of each function. And the domain is going to have a lot to do with this vertical asymptote. So for our domain, we're going to want basically all real numbers except x equal 3, because that's where the function is not defined, hence where the asymptote is. But it can actually be 0 in this case, and it can be any negative number and positive number except for 3. So there's our domain. Our range is going to be all reals. Again, it can be negative below the x-axis, it can be positive above the x-axis. It just can't equal 0. So all reals except y equal to 0. Y will never equal 0, which is why you have your asymptote there. So it's important for you to understand that relationship between the asymptotes and the domain and range. So now let's go to part B. And likewise, we're going to draw in our asymptotes. It looks like this time, if you look at the x plus 2 here, that's going to give us an asymptote of x equals negative 2. So I'm going to go ahead and draw in that asymptote so you can see it there. But this time, because of this minus 1, we're actually going to see that the graph actually dipped below the x-axis, and it looks like we have an asymptote right here, a horizontal asymptote. So now we need to make sure that we list those. So for our vertical asymptote, in this case, we're going to have x equals negative 2. Our horizontal asymptote is going to be y equals negative 1. And then we're going to have domain and range issues. Okay, so your domain is going to be associated with your vertical asymptote. So it's going to be all reals except, so for the domain you can have negative values, positive values, you can even have 0, you just can't have negative 2. So all reals except x equals negative 2. And for your range, you can have all reals except y equal to negative 1. So again, you can see the relationship between vertical asymptote, domain, horizontal asymptote, and the range. All right, so now we're going to have you try this do-it-yourself question. And again, if you want to look, I tried drawing in your asymptotes for you, but if you want a better looking graph, you can find it on page 546. In example 3, we're going to basically put all of this stuff together. You heard me mention a little while ago about the minus 1 and how that affected the graph. But basically what you're seeing here is transformations. We did them in quadratics, we did them with absolute value, and we're doing it again here with reciprocal functions. Basically, anytime you have a number inside of grouping symbols, we mentioned earlier that our parent function was 1 over x. So when I say inside of grouping symbols, this is the equivalent to when you had x squared, and then you had f of x equals x plus 1 squared. So the plus 1 was inside the grouping symbols, and the minus 3, for example, could be outside the grouping symbols. The one inside the grouping symbols basically dictated whether it was shifting left or right, and the negative dictated whether it was going up or down. Sometimes you could have a number in front, which would either stretch it vertically or compress it vertically. And you could also have, if it was negative, it would be upside down, and so on and so forth. So the same thing is happening with reciprocal functions. If you have something inside the grouping symbols, in this case, the grouping symbol is not parentheses. In this case, the grouping symbol is the fraction bar. So the x minus 4 is all under the fraction bar. So this minus 4 means that my graph is going to shift 4 units to the right. And then the plus 2, because it's not underneath the division bar, is actually going to act as a vertical shift of 2 units up. And then the 2 in front is going to be like the number that you would put in front of the parentheses, because I could rewrite this function as 2 times 1 over x minus 4 plus 2. So the 2 is kind of like that vertical stretch factor. And again, if it was positive or negative, it would basically invert your hyperbola. We saw earlier that the hyperbola normally looks like this. If it was a negative 1 over x, you would invert your hyperbola and you would have this kind of a graph happening. So all of those things are still happening or applying to reciprocal functions. And so now we're actually going to take this information and we're going to try to graph this little guy. So we know the parent function looks we know what the parent function looks like, and we know now that this is going to be a shift to the right of 4 units and a shift of 2 units up, and that's going to affect our asymptotes, because our asymptotes are also going to shift with it. And then we also have a stretch factor of 2. So that means that we are going to now graph this little guy. And it doesn't have to be a perfect graph, but the things we just mentioned should definitely be present in your graph. So here we go. What we're going to see is, first off, I like to always graph my asymptotes first. It makes it easier for me. This 4 minus 4 means I'm going to shift 4 units to the right. So 1, 2, 3, 4, 5, 6, so to speak. And then we're going to go 1, 2, 3, 4, 5 over here. And 1, 2, 3. Okay, so what I'm going to do is I'm going to go ahead and draw in my vertical asymptote, which I know is going to be 4, because the x minus 4 equal to 0 is going to be x equals 4. So 1, 2, 3, 4. And I'm going to go ahead and just draw in my vertical asymptote. Just like that. And also, this plus 2 is going to shift my horizontal asymptote, which used to be here at the on the x-axis. Now it's going to move up 2 units as well. So I'm going to go ahead and do this. And there we go. So basically what's happening now is that this intersection of my asymptotes is kind of like my new origin. If I can think of this as my new origin, when I draw the parent graph, I know it's going to be something like this and like this. But this vertical, this 2, which is stretching it vertically, is going to affect my result just a little bit. So if you want, at that point, you could plug in, you can just, in your head or on some paper, you can take, this is for, what would happen if the x coordinate was a 5 or a 6. So if it was a 5, 5 minus 4 would be 1, and you'd have 2 over 1. And then 2 plus 2 is 4. So when x is 5, y is 4. So we're going to go 1, 2, 3, 4. We'll just do it right here. Normally you would have that value be here, but because it's this 2, it's actually a little bit like this. Oops, we don't want it to be dashed, we want it to be solid. So let me get my solid over here. And you're going to have your other part of the graph over here. I'm not really picky about the exact values, but I do want to make sure that I see your vertical asymptote where it's supposed to be, your horizontal asymptote where it's supposed to be, and that the graph, that the branches, like whether it's positive or negative, are in the right spot as well. Alrighty, so that's a brief graph of that function. So now we're going to go over here and we're going to do the same thing. So what you're going to see in this case is the +1 is going to shift our graph 1 unit to the left this time. The -4 is going to shift it 4 units down. And because it's a -3, not only is it going to have a vertical stretch factor, it's also going to be inverted. The branches are not going to be in the top right and the bottom left. They're going to be in the top left and bottom right. Okay, so we're going to go ahead and graph this little guy. Okay, so again, one of the first things I like to do is to draw in my asymptotes. So because this is going to have a -1 asymptote vertically, I'm going to go ahead and come over here and draw that in first. So there we go there. And the -4 is going to shift my graph 4 units down. So there's 1, 2, 3, 4 units down, right about there. And so again, my intersection here is going to be my new origin, so to speak. And normally I would put my branches here and here, but because it's negative, I'm actually going to put my branches over here and over here. Okay? And the 3 is going to stretch it vertically, and if you want to get more precise values, you can always test a point. In the interest of time, I didn't do that, but you can always make sure that you just pick a point to the right or left of your asymptote, and you can plot that point so you can get that stretch factor going on. But the other thing that we have to do in this example is to state the domain and range. And we said earlier that the domain and range are tied very closely to the asymptotes. So domain for part A would be all reals except x equal to the vertical asymptote, which was 1, 2, 3, 4, so x cannot equal 4. And then for our range, it's going to be all reals except y equal to 2. So y cannot equal 2 and x cannot equal 4. And then for part B, our domain is all reals except x equals to -1, and because of that vertical asymptote. And then for the range, it'll be all reals except y equal to -4, which was your horizontal asymptote down here. Okay, so now you can try these 2 examples, and then we'll go to our last example. And it says an airline has a daily non-stop flight between Los Angeles, California and Sydney, Australia. A one-way trip is about 7,500 miles. In part A, it says write an equation that represents the travel time from Los Angeles to Sydney as a function of flight speed. Then I want us to graph the equation. Now again, in the interest of time, I'm not going to graph the equation, but I am going to give you the equation. or help you come up with the equation. We have a formula that we kind of use to relate distance with time and speed, because it wants the flight speed. And that formula, you might remember, is distance equals rate times time. However, they want an equation that represents the travel time. That means that they want me to take this equation or this formula and transform it so that it says t equals instead of d equals. So to do that, I would divide by the rate, and then I would get t is equal to distance divided by rate. And I know the distance because it was given. A one-way trip is about 7,500 miles. So now if I plug that in, I get t equals 7,500 divided by r. And so it says here they want an equation that represents time as a function of speed. And that's exactly what I have here, time as a function of speed. All right, so our part A is done. And then it says in part, they want us to graph the equation, so you can graph it in your notes. But and you can use your calculator to help you do that. You're going to need a lot bigger window because of the 7,500. I suggest that you go from maybe 1,000 on x-axis, go from negative 1,000 to positive 1,000. And then on the y-axis, you can go from maybe negative 100 to positive 100. That'll give you a nice window in your calculator to graph that function. Part B says, explain any limitations to the range or domain in this situation. And that we can do because we know how to deal with asymptotes. We know that this function is going to have a vertical asymptote when r is 0, because you can't have division by 0. So r cannot equal 0. But beyond that, because this is a real-life application, we can't even allow our r variable to be negative, because that would be a negative flight speed, and that wouldn't make any sense. Okay, so in this case, you're kind of confined not only by the asymptote, but also by the practicality of this situation being a real-life situation. So in this situation, the range and domain are limited to all real numbers greater than 0. So we want domain r greater than 0. We don't want it to equal 0. Our range has to be greater than 0 because it wouldn't make sense for the time. Sorry, that should be a t. Our range is the t variable. Okay, so t has to be greater than 0 because we don't want time to be negative either. And on top of that, you have further restrictions because the aircraft itself is going to have maximum and minimum speeds at which it can travel. That wasn't given in the problem, but as far as like explaining limitations, this is the limitations that you have just because you want it to not be negative. But on top of that, you have to keep in mind that the aircraft that is flying here also has limitations. It can't go as fast as it wants. It has, limitations to its motor and blah, 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 blah. So that's what we have for part B. So now if you will try example 4, once you have done this do-it-yourself question, you will have completed your notes for this lesson, and I will see you in class. And thanks for watching.